Concrete can have a corrosive effect on bare copper due to the presence of moisture and alkalinity. This can lead to the degradation and weakening of the copper, reducing its conductivity and increasing the risk of failure. 250.52 A3 defines a conductive envelope enclosure as an enclosure that surrounds and is in intimate contact with the bare copper conductor. It must firstly be constructed of a material suitable for the intended use and environmental conditions, secondly, provide a continuous and effective electrical path, and thirdly, ensure that the conductor remains protected from physical damage and corrosion. The requirement for a conductive envelope enclosure is intended to enhance the protection of bare copper conductors from concrete by providing a conductive path that minimizes the effects of corrosion and ensures a reliable electrical connection. Exhibit 250.22 shows a sleeve or boot used to provide protection for the bare copper conductor as it emerges from the slab. This sleeve extends a sufficient distance beyond the concrete surface to provide a visible portion for examination and connection. The inspector's requirement for an accessible connection is based on 250.126c, which states that all connections shall be accessible. In this context, accessible means that the connection can be readily inspected, tested, and worked on when necessary. Exception number 1 to 250.6d8 allows for the grounding connection to be within the concrete if it is firstly embedded at least 12 inches from the nearest edge of the concrete, and secondly, exceptionally unlikely to be disturbed or subjected to physical damage. This exception applies to the actual grounding connection, not to the conductive envelope enclosure that protects the bare copper conductor. Conductive envelope enclosure requirements are intended to enhance the current grounding requirements by providing additional protection for bare copper conductors in concrete. They do not replace the existing requirements for grounding. The purpose of a conductive envelope enclosure, or CEE, is to provide a protected and reliable electrical connection when using bare copper conductors in concrete. Concrete can be corrosive to copper due to its moisture content and alkalinity. This corrosion can degrade the copper, reducing its conductivity and increasing the risk of electrical failures. A CEE addresses this issue by creating a conductive path around the copper that isolates it from the corrosive effects of the concrete. The construction of a conductive envelope enclosure involves several key elements. Firstly, the material used for the enclosure must be suitable for the intended environment. This means it should be resistant to moisture, chemicals, and physical damage. Typically, materials like PVC or other non-conductive plastics are used for the outer layer, while the inner layer, which comes into direct contact with the copper, needs to be conductive. Secondly, the enclosure must provide a continuous and effective electrical path. This ensures that the grounding system remains functional even if the copper conductor is compromised. The conductive layer inside the enclosure helps to maintain this electrical continuity. Thirdly, the design of the enclosure must protect the copper from physical damage and corrosion. This involves ensuring that the copper is completely encased and sealed within the protective layers of the enclosure. The sleeve or boot shown in Exhibit 250.22 serves this purpose by providing a barrier against the surrounding concrete. The sleeve extends beyond the concrete surface, allowing for a visible inspection point. This is crucial because it allows electricians and inspectors to examine the condition of the copper without having to break into the concrete. The sleeve should extend far enough to facilitate easy access for testing and maintenance. Accessibility of connections is a critical requirement in electrical installations, as emphasized in 250.126c. The term accessible means that the connection can be readily reached for inspection, testing, and maintenance without damaging the building structure or finish. This ensures that any issues with the grounding system can be quickly identified and addressed. Exception number 1 to 250.68 provides a specific allowance for grounding connections embedded within concrete under certain conditions. This exception states that the grounding connection can be encased in concrete if it meets two criteria. Firstly, it must be embedded at least 12 inches from the nearest edge of the concrete. This depth helps to protect the connection from physical damage and environmental factors. Secondly, the connection must be exceptionally unlikely to be disturbed or subjected to physical damage. This means that the connection should be in a location where it is unlikely to be impacted by construction activities, heavy equipment, or other potential sources of damage. However, it is important to note that this exception applies specifically to the grounding connection itself, not to the conductive envelope enclosure. The conductive envelope enclosure should still be accessible for inspection and maintenance, even if the grounding connection is encased in concrete. The requirements for conductive envelope enclosures are intended to enhance, not replace, existing grounding requirements. This means that the conductive envelope enclosure provides an additional layer of protection for bare copper conductors in concrete, ensuring a more reliable and robust grounding system. Grounding systems are designed to provide a low impedance path for fault currents, which helps to protect people and equipment from electrical hazards. By enhancing the protection of bare copper conductors, conductive envelope enclosures contribute to the overall effectiveness of the grounding system. In summary, conductive envelope enclosures are an important component of modern electrical installations, particularly in situations where bare copper conductors are used in concrete. They provide a protective barrier against corrosion and physical damage, ensuring the reliability and longevity of the grounding system. When installing conductive envelope enclosures, it is important to follow all applicable codes and standards, including 250.52 A3, 250.126C, and 250.68A. Additionally, it is crucial to use materials that are suitable for the intended environment and to ensure that the enclosure is properly installed to provide a continuous and effective electrical path. By taking these steps, you can help to ensure the safety and reliability of your electrical system. Understanding the requirements and proper installation techniques for conductive envelope enclosures is essential for ensuring the safety and reliability of electrical systems, especially in environments where concrete and bare copper conductors interact. The corrosive nature of concrete necessitates protective measures to prevent degradation of the copper, maintaining its conductivity and minimizing the risk of electrical failures. This understanding extends to the specific provisions within the National Electrical Code, or NEC, such as 250.52 A3, 250.126C, and 250.68A, which outline the standards for conductive envelope enclosures, accessible connections, and grounding connections, respectively. A conductive envelope enclosure is not merely an accessory, but a critical component that provides a barrier between the bare copper conductor and the surrounding concrete. Its primary function is to prevent the corrosive effects of moisture and alkalinity present in concrete from degrading the copper. By encasing the copper within a protective layer, the conductive envelope enclosure ensures that the conductor maintains its conductivity and structural integrity over time. The construction of a conductive envelope enclosure involves careful selection of materials and precise installation techniques. The materials used must be resistant to the harsh conditions present in concrete environments, including moisture, chemicals, and physical stress. Typically, the enclosure consists of multiple layers, with an outer layer made of non-conductive plastic or PVC to provide insulation and protection against physical damage, and an inner layer made of conductive material to maintain electrical continuity. The design of the enclosure must ensure a continuous and effective electrical path. This means that the conductive layer must be in direct contact with the copper conductor and must extend throughout the entire length of the enclosure. Any gaps or discontinuities in the conductive path could compromise the effectiveness of the enclosure and increase the risk of electrical failures. The installation of a conductive envelope enclosure requires meticulous attention to detail. The enclosure must be properly sealed to prevent moisture from penetrating and corroding the copper conductor. All connections must be secure and properly insulated to ensure a reliable electrical connection. Additionally, the enclosure must be installed in a manner that protects it from physical damage, such as impacts from construction equipment or other sources. Accessibility of connections is another critical consideration in electrical installations. As stated in 250.126C of the NEC, all connections must be accessible for inspection, testing, and maintenance. This means that the connections must be located in a place where they can be readily reached without damaging the building structure or finish. In the context of conductive envelope enclosures, accessibility typically means that the enclosure must extend beyond the concrete surface, allowing electricians and inspectors to visually inspect the condition of the copper conductor and make any necessary repairs or adjustments. Exception number 1 to 250.68 provides a limited exception to the accessibility requirement for grounding connections encased in concrete. This exception allows grounding connections to be embedded in concrete if they meet specific conditions. Firstly, the connection must be embedded at least 12 inches from the nearest edge of the concrete. This depth provides a degree of protection against physical damage and environmental factors. Secondly, the connection must be exceptionally unlikely to be disturbed or subjected to physical damage. This means that the connection must be located in a place where it is unlikely to be affected by construction activities or other potential sources of damage. However, it is important to emphasize that this exception applies only to the grounding connection itself, not to the conductive envelope enclosure. The conductive envelope enclosure must still be accessible for inspection and maintenance, even if the grounding connection is encased in concrete. The requirements for conductive envelope enclosures are intended to enhance, not replace, existing grounding requirements. Grounding systems are designed to provide a low-impedance path for fault currents, which helps to protect people and equipment from electrical hazards. By enhancing the protection of bare copper conductors, conductive envelope enclosures contribute to the overall effectiveness of the grounding system. This is because bare copper conductors, when exposed to the corrosive environment of concrete, can degrade over time, reducing their conductivity and increasing the impedance of the grounding path. By protecting the copper from corrosion, conductive envelope enclosures help to maintain the integrity of the grounding system and ensure that it functions properly in the event of a fault. In addition to protecting against corrosion, conductive envelope enclosures also provide a measure of physical protection for the copper conductor. This is important because bare copper conductors can be easily damaged by impacts or abrasion, which can compromise their conductivity and increase the risk of electrical failures. By encasing the copper within a protective enclosure, the conductive envelope enclosure helps to prevent physical damage and ensure that the conductor remains in good condition. Overall, conductive envelope enclosures are an essential component of modern electrical installations, particularly in environments where concrete and bare copper conductors interact. They provide a protective barrier against corrosion and physical damage, ensuring the reliability and longevity of the grounding system. When installing conductive envelope enclosures, it is important to follow all applicable codes and standards, including 250.52 AFRI, 250.126C, and 250.68 of the NEC. Additionally, it is crucial to use materials that are suitable for the intended environment and to ensure that the enclosure is properly installed to provide a continuous and effective electrical path. By taking these steps, you can help to ensure the safety and reliability of your electrical system and protect people and equipment from electrical hazards. The effectiveness of conductive envelope enclosures hinges on several factors, starting with the correct material selection. The choice of materials dictates the enclosure's resistance to environmental stressors and its ability to maintain electrical continuity. For the outer layer, materials like PVC or other non-conductive plastics are preferred due to their excellent insulating properties and resistance to moisture and chemicals. This outer layer serves as a primary barrier against the corrosive elements present in concrete. However, the inner layer, which is in direct contact with the copper conductor, requires a conductive material. This ensures that there is a continuous electrical path, even if the copper conductor experiences some degradation over time. The conductive material used for the inner layer must be compatible with copper to prevent galvanic corrosion. Proper installation techniques are just as critical as material selection. The enclosure must be sealed effectively to prevent any moisture from seeping in and causing corrosion. This often involves using specialized sealants and adhesives that are specifically designed for use in concrete environments. The connections within the enclosure must also be secure and properly insulated to ensure a reliable electrical connection. Any loose connections or inadequate insulation can lead to electrical failures and compromise the effectiveness of the grounding system. Regular inspection and maintenance are essential for ensuring the long-term performance of conductive envelope enclosures. During inspections, electricians should look for any signs of damage or deterioration, such as cracks, punctures, or corrosion. They should also check the connections to ensure that they are tight and properly insulated. If any problems are detected, they should be addressed promptly to prevent further damage and maintain the integrity of the grounding system. In addition to visual inspections, electrical testing should also be performed on a regular basis to verify the continuity and resistance of the grounding path. This can be done using specialized test equipment such as ground resistance testers and continuity testers. These tests can help to identify any hidden problems with the grounding system, such as corroded connections or damaged conductors. Proper grounding is fundamental to electrical safety, and conductive envelope enclosures play a vital role in ensuring the effectiveness of grounding systems in concrete environments. By providing a protective barrier against corrosion and physical damage, conductive envelope enclosures help to maintain the integrity of the grounding path and prevent electrical hazards. The requirements outlined in the NEC, such as 250.52A3, 250.126C, and 250.60A, provide clear guidelines for the design, installation, and maintenance of conductive envelope enclosures. By following these guidelines, electricians and installers can ensure that their grounding systems are safe, reliable, and compliant with industry standards. In conclusion, understanding and implementing best practices for conductive envelope enclosures is paramount for electrical safety in concrete environments. It requires a comprehensive approach that encompasses material selection, installation techniques, inspection and maintenance, and adherence to industry standards. By adopting this holistic approach, we can ensure that our electrical systems are protected from corrosion and physical damage, providing a safe and reliable environment for people and equipment.